Okay, so the second presentation for today is by Anna Chernyshova, two and three-dimensional effects of evolution with waves and something generated. Is it theoretical work?
It is partially theoretical and partially experimental work.
So you did experiments?
Yeah.
Okay. Please.
Hello, my name is Anna. I'm making my PhD under the supervision of Professor Lev Shemer in Tel Aviv University. And today I will make a talk about part of my PhD work, which is now in progress. I'm in the middle of the track, about two- and three-dimensional waves. So what it will be about. We have two-dimensional waves which are more easy to understand because we can generate them by the wave maker in the lab, and they don't change in the cross-section, only along the tank. They have more regular structure, so we can measure them by wave gauges and some not very complicated instruments. And there are numerous models to describe the behavior and the evolution, the spatial and temporal evolution of 2D waves, so they are more comfortable. And we have 3D waves, which are the usual process we see in the ocean and in the sea and the other water reservoirs, which are not so nice thing to easily explain because they have three-dimensional structure and you can't just measure them along the tank. You have to measure them in both cross-section and along the wave tank sections. In the lab, we generate them with the wind, and the process is pretty random with a huge effect of randomness. So those waves are usually studied by statistical techniques. In this work, we're getting two-dimensional waves, which I will start from. I will talk about linear instability analysis, which is a theoretical part of the work, based on Zakharov equation, which serves the base for this study. And then in the Zakharov equation, we have nonlinear interaction mechanisms. And on the base of it, I made some numerical simulations to compare with experiment I made in the wave tank. And the other part of work is now in the beginning, where I study fully wind-generated waves combined with some mechanically generated waves, which we know how to then we know their evolution. So let's start from theoretical part. I will talk a little bit about temporal form of Zakharov equation, which is the original one derived by Zakharov in 1968 for infinitely depth water, and then by Zakharov and Haritonov for arbitrary depth of water. My advisor, Lev Shemer, with Michael Chasny, rederived the Zakharov equation in temporal form for finite water depth, and I show here some formulas from the paper of 1984. Basically, how the Zakharov equation is constructed. So we have governing equations like Laplace equation, kinematic and dynamic conditions, and conditions on the bottom. Using Fourier transform with some cumbersome computations, they receive the form of Zakharov equation, which is, I hope, well known here, where B is complex amplitude of the waves, K wave numbers, and T here is interaction quartet coefficients. And delta is delta Dirac. So this equation shows how the waves will interact if we take a quarter of the wave. Like the quarter wave interactions are the smallest order possible interactions. And their amplitudes will interact with each other and make the evolution of the waves in the temporal domain. So this is how waves changes with time. Class 1 linear interactions require the coexistence of nearly resonating quartets. This means that we take 4 waves with the wave numbers k, k1, k2, k3, and they should be this condition fulfilled. And according to nearly resonating wave particles condition, we also have condition on omegas, on the frequencies, which should be almost like this, but not equally zero, but small enough. So that means that the waves should be, the frequencies of the waves should be close enough to interact. So this is the discretized form, which is Chastain and Chamber also derived in their paper. Here we have three waves, two of which is taken twice, which are named here by indices A, B, and C. So we take twice A wave, and in discretized form, the Harf equation looks like this. But we are interested in comparing these with experiments. If we take the temporal form of the Harf equation, there is condition of spatial periodicity, which is hardly fulfilled in a wave tank, because we can't just make waves in two different points behave absolutely periodical and the same. But we can do in the wave tank with a wave maker, we can make temporal periodicity of the waves as we take in the different points of time, in the same points of space, the wave will behave the same. So Schemer in 2001 and 2002 derived spatial version of the Harf equation, which is actually made from temporal form using periodicity in time. So here it looks almost the same, very similar, but we have here different derivative in x, so we have spatial evolution, and we take the quarters which fulfill a little bit different conditions, so it is exact resonance on frequencies, and on k it is near resonance. Also we have here Cg, which is group velocity of harmonic for what we write the equation of G harmonic, and V is actually the same from the previous equation, which is T. It is quartet interaction coefficients derived by Krasitsky in 1994. So this is again the near resonance condition for wave number in spatial case. We need that K should be close enough, but not equal zero. This formula shouldn't be equal to zero. And using numerical simulations to understand what is this, which is the parameter, how close k should be to each other, we just derived it empirically, defined it empirically like this, like the mean wave number. So in my experiments, we use the intermediate depth linear spatial relation, which I think you all know. And we perform instability analysis. So there's such a thing as Benjamin-Fehr instability, which claims that if we take one carrier wave with significantly big amplitude, and on the side of it, in the temporal domain, two sidebands with a small, infinitesimally small amplitudes on the equal distance, that means that there is some kind of maximal growth rate step between carrier and sidebands, and if we put sidebands on this distance, that means that they will significantly grow, like in an exponential way, with time. And temporal analysis to find these steps between wave numbers of carrier and of sidebands was performed by different authors, and this is like fully theoretical investigation. But as we can compare in spatial form, we can compare the results with experiments, so that's what we did with my advisor. We made the same thing for spatial the Harf equation to see, is it Benjamin-Fehr instability a real mechanism of growing of sidebands? So if it is like this, we will find some distance between carrier frequency and two disturbances which are small enough, and then in some space they will grow infinitely. So this is how we do instability analysis. Remember, we had the Harff equation, and there were amplitudes B. Here I call it B0, which is carrier wave, and B minus and B plus, which are amplitudes on the both sides of the frequency. So we have initial conditions here, and to make a linearization process, we say that the amplitude, B, here it is, these amplitudes, of sidebands are much smaller than the amplitude of the carrier. So that help us in the Zaharov equation to throw away every term which consists of second or third power of very small values. So after linearization, we can solve the equation, and this is what we have for solution. We can see here that this is the amplitude of carrier wave, which is not so drastically changing, and those amplitudes of the sidebands, they have here some delta, this which will make exponential grow if the power of exponent is big. So in order to find where the growth will be the fastest, we need to make this term in a high power. So it happens then discriminant here is very, very small and negative. So growth rate, this is the dimensionless variable value that shows how fast waves sidebands will grow on a certain frequency step around carrier. And on this picture you can see the dependence of dimensionless growth rate and on the frequency step. Here delta omega divided by delta 0, where delta 0 is carrier wave frequency and delta omega difference, frequency difference between carrier and sidebands. Different curves shows dependency of dimensionless growth rate for different steepnesses epsilon, which is A amplitude and K wave number of the carrier waves. And you see there is a peak values on each curve that denotes maximum growth rate. In our experiments, we took epsilon 0.21 because on this scale we have enough waves in the wave tank in the experimental area, but they are not too steep in order not to have wave breaking, and which can affect somehow our measurements. So here you can see that the peak value is 0.225 something here in between, and that should mean that if we take frequency step, like relative frequency step near this value, that means that our sidebands should grow exponentially, and we would see this in experiments. But is it really true? We will check in the container. We checked it actually. So this is one of our facilities in the lab. A huge wave tank of 18 meters long, but we use only 15 meters because they are, although we have energy absorbing reach on one side, still there are some reflections, so we use only 15 meters. And the water wave here is 60 centimeters. On one side of the container we have, as I said, energy absorbing reach, which prevents reflections. And on the other side we have wave maker, which is closer pictures here. It is flap type wave maker consisting of the 4 flaps, which can move simultaneously or with a different phase, but we use it simultaneously as one huge wave maker because we need 2-dimensional waves. And we have here a carriage with wave gauges on it, 4 wave gauges, 40 centimeters between each of them, and we can move the carriage measuring the surface elevation by the wave gauges in different points of the wave tank. We made here 32 points, 40 centimeters between each, and experiments were just made. We made a signal on the wave maker, then we moved the carriage in one point, recorded data, then move it a little bit, then move wave maker again, and we had 32 points like this. So this is how experimental procedure was constructed. We decided to start measurements with simplest spectrum which are like bimodal spectra with initially equal harmonics. You can see here on this picture this spectrum, and initial spectrum here is red dots. So you have here only two harmonics, and we call this like in the between of them. This is a carrier which has 0 amplitude, and we just took two of them. But when we start to measuring it, say on near the wave maker, we have 160 on the distance of 160 centimeters. We receive this spectra, which is denoted by blue triangles, and you see the harmonic on the high frequency side of the spectra starts growing. And on this picture, you see the surface elevation. So red, you see red envelope is very symmetric, very nice and smooth. And blue envelope is on 160 centimeters, and it's a little bit not a symmetric shape already. But when we put the bimodal spectrum to the wavemaker, we also have to remember that near the wavemaker there are evanescence modes, which we don't want to take into account because they die not very far from wavemaker, but still we already have sensors there. So what we did, these pictures are actually simulations pictures because we used it. We decided let's make two model spectrum not on the wavemaker but near it in 160 centimeters to prevent having evanescent mode from the wavemaker. So we just took the Harf equation and integrated it backwards. What we have to put to the wavemaker to obtain fully bimodal spectrum near it, not on the wavemaker but near it. So we just shifted 0 on the 160 centimeters. Okay, so these are already data which I received from experiments compared with numerical simulated data, which we use like the Harf equation, which is numerically solved. And here solid red lines are measured data, and dotted black lines is from simulations. You see here pictures how surface elevation differs with distance. So this is on 160 centimeters, as I said. You put only two modes, and this how they will change, how the wave packet will change with distance. Here you see the same, but for different frequency steps between initial two modes. So this is here you have 10 waves, 10 small waves in a big packet. Here you have 32. So this means that they're closer harmonics. Here also you can see that it is the picture is not symmetric above the x-axis, so you have here a little bit bigger values than you have here. This is because we have bound waves, which occurs on the frequencies higher than the usual one. So if we have frequency, say omega, bound waves will be on 2 omega, 3 omega, and further. So we don't have this in simulations, but we have this in experimental data. So we just put it afterwards plus to the simulations to compare it nicely. And also here you can see that the maximum of envelope changes with distance. So here it's not that big, and in the end of the container it's big enough here. We also will see how it changes with distance. So spectral evolution for initially bimodal wave trains of initially two equal amplitudes are presented in this picture. And we see here that the closer are the initial harmonics to each other, the more interactions we have. So here I must highlight that when make simulations, we allowed a number of waves around carrier frequency to change, to move. So we put it into calculations. But you see that in this part of spectrum nothing occurs, just because in the model there are these waves, but they are not affected by nonlinear interactions. And we see the closer are the waves, the more interactions in the high frequency part of the spectrum. We also made similar investigations for initially bimodal spectrum with different amplitudes of two waves to see how it will affect, and we had also proved that the closer are initial amplitudes to initial frequencies to each other, the more interactions there will be. And also a spectrum of one carrier wave with a big amplitude and one or two sidebands with a small amplitude, like 1/10 of the carriers. And this can be considered as Benjamin-Fair instability, like connected with Benjamin-Fair instability analysis it was before. And if we put the difference, the frequency step, according to the most unstable mode growth, there should be exponential growth, but we didn't see this in experiments. So we also looked at how amplitude changes with distance of these two-dimensional spectra. So here on the pictures I put two initial amplitudes that we have there, with two frequencies, two initial amplitudes, and on the side of them, one step on the left part of the spectrum and on the right. You can see that here the discrepancy between experimental and simulated data is not that big. And we can see here also the growth of maximal values of crests and minimal values of troughs and maximum values of the envelopes if we change the frequency width. So this is wider spectrum, this is narrower spectrum. And you can see that from the beginning to the end, the maximum crest values changes almost twice. So that means there can be some kind of connection with generation of rogue waves. But the spectrum must be narrow enough to big rogue waves to be generated. Also, we have a container, well, long, but not so long. 15 meters is good if you want to see how the waves evolves in the beginning. But if you want to see bigger distances, like 100 meters, 200 meters, we don't have such a facility. But we saw that simulations are pretty good with experiments comparison, so we decided to make just numerical simulation and see how these harmonics will behave on long distances. Like here it's, here's 120 wavelengths, and the carrier wavelengths in our facility was 77 centimeters. So we see if we took the wide spectrum, we have almost periodic changes of amplitude here, and the energy is almost conserved. So here the green line is the energy of all the waves that we allowed to change, and orange line is the energy of only those four waves, which are two initial ones and two by sides. And you see when the spectrum is wide, there's no big difference between the energy. It means no many new harmonics were born. And we have here almost ideal Fermi-Pascal recurrence. As we make spectrum narrower, we see that some energy is transmitted to the higher frequency part of spectra. And here we see that the full energy, which is green, differs from energy of these four waves. And as we make spectrum narrower and narrower, we see that many harmonics, new harmonics occur, and the behavior of initial ones are not regular and they're not periodic anymore. And this shows that actually in the spectrum with frequency step close to maximum growth rate, frequency step from Benjamin Fair instability analysis shows even less interactions between harmonics and not significant growth of sidebands. So the mechanism of growing of sidebands is mostly nonlinear, and it's good enough described by Zakharov equation model, but Benjamin Fair instability is not so significant here. So next step, I would like to talk about wind waves, which are three-dimensional, and I will start from describing the facility what we have in the lab. This is a smaller wave tank. 5 minutes, okay. This is a small wave tank. Here you have two different sides of it. On the one side we have wave maker, not of the flat type, but it only wedge type, which goes up and down. We have a wind flume, which is closed cycle, closed loop. So we make wind here, and various sensors, which is laser slope gauge and also wave gauge, as in the previous wave tank, and movable instrument carriage with pitot tube to measure pressure of the air and of water. So this I would really show how it looks. This is the video of my lab mate. He recorded the evolution of the waves of the wind, fully wind waves in the small container with distance. So you see here in the picture on the low left corner how the camera moves along the wave tank and how the pattern of the waves changes with distance. But these are only wind waves, no mechanically generated simple spectrum harmonics. Okay, so to measure the three-dimensional structure of the waves, we have laser slope gauge here, which is consisted just of the laser under the wave tank, and the beam of the laser deflects when meet a wave, goes through Fresnel lens to the diffusive screen, and the Fresnel lens put the laser beam in exact point for the waves with the same steepness. So it doesn't matter how high the waves are, there's only one point for each steepness on the diffusive screen. So this is how Fresnel lens look like. This is the ordinary lens, and Fresnel lens is just cut it ordinary lens like this, so it's flat and small and it's easy to operate. And it doesn't matter which is the height of the wave, with the same steepness, the Fresnel lens will take the beam on the same point on the screen. So having the point on the screen, we know exactly what the steepness was of the wave. And this instrument is two-dimensional, so we can measure steepness along the wave tank and the cross section as well. So we have just dieta dx and dieta dy components. So here we'll show you how exactly the laser beam dances on the diffusive screen. And there's a sensor, position sensor above it, which records the position of the laser. And then we can see what was the slope. Okay. So these are preliminary results of the one experiment that I did. The idea was to see if we at first use only wavemaker and make only simple narrow spectra, say one sinus wave, how it will behave. And then if we put only wind waves without any mechanical generated waves and see what is the dominant frequency of these waves. And then if we combine them together, mechanically generated and wind generated waves, what will be the spectrum of this combinated system. And it turned out that here, as we took very small amplitude of wave maker, and this is only one harmonic, we try to make one harmonic, and the black dots are wind wave spectrum, which is pretty wide, and the dominant frequency is here somewhere around 4 Hertz. And then we combined it, we saw that the red dots shows the combined spectrum, and not only the frequency peak of wind wave shifted to the low frequency part, but also the amplitude enhanced more than 8 times. So this will be the second part of my work that I will perform during my next year of the PhD. And I would like to see what are the different effects of mechanically generated wave of different frequency on the wind generated waves. And we can combine different dominant frequency of them and see how they behave. So here, this was the table that I did for experiments with a different wind speed, different frequency of the wave maker, different amplitudes of the wave maker, and of all these combined. Those are just dominant frequency, but from this picture we can see easily that the higher the wind, the smaller the dominant frequency of the combined system. And we can see that if we take very high frequency of the wave maker, it doesn't affect much. So at amplitude, with the same amplitude, we have same frequency, same dominant frequencies with a high frequency. So these will be next steps of my work to investigate how this system behaves, and are there more influent mechanisms of linear mechanisms of evolution or non-linear mechanisms of evolution. So that's it. Thank you.